Welcome to the deep dive. Today, we're tackling a subject that's, well, absolutely vital for keeping aircraft safely in the sky, the lubrication and cooling systems within their engines.
Yeah, we'll be looking at both the piston engines and those incredible turbine power plants.
Exactly. We've got some really detailed material here, and our goal, really, is to extract the core knowledge about how these systems prevent damaging friction, manage intense heat,
And ultimately keep these complex machines running powerfully and reliably, all without getting lost in, overly complicated jargon.
Okay, let's get started with lubrication. It really is the engine's lifeline, isn't it?
Absolutely.
The basic problem, as you know, if you've ever rubbed your hands together to warm them up, is friction.
Right. Picture two metal parts constantly rubbing directly against each other inside an engine. It sounds bad, and it is.
Yeah, our sources illustrate this, showing those tiny microscopic imperfections on the surfaces, creating resistance.
And the key solution? Oil. That amazing flippery film that gets between those moving parts.
It creates a buffer, preventing that destructive metal-on-metal contact.
And what's fascinating is that by introducing this oil layer, we're essentially replacing that harsh friction between solids with the much gentler internal friction within the oil itself.
Ah, okay.
This makes a huge difference. It leads to more power and, crucially, less unwanted heat being generated. Think of it like gliding instead of grinding.
Gliding instead of grinding. I like that. Now, when we say friction, it sounds like there are different kinds at play inside an engine.
There are indeed. The type depends on how the parts interact. First, we have sliding friction.
Okay.
That's in plane bearings, where one surface just glides over another. Even though they might look smooth, those microscopic bumps we mentioned create resistance.
Then there's rolling friction, which you find in ball and roller bearings, often called anti-friction bearings.
And for good reason, precisely. When a ball or roller moves over a surface, the friction produced is much, much less than with sliding.
Makes sense.
That clever design with inner and outer rings and the rolling elements in between really minimizes energy loss.
And finally, wiping friction. That happens between gear teeth.
Yes, and that must be under tremendous strain, considering the power being transferred.
You bet. Gear teeth experience immense pressure as they mesh and drive components.
So the lubricant in this case has to be incredibly strong to withstand these extreme loads and prevent direct contact, ensuring smooth and efficient power transmission.
So oil is the ultimate friction fighter, but it sounds like it has a whole lot of other jobs, too.
Absolutely. It's not just about reducing friction. The oil film acts as a vital shock absorber.
Shock absorber, how so?
Well, think about the immense forces acting on a crankshaft and connecting rods with each power pulse. Bang, bang, bang.
Right.
The oil cushions those impacts, preventing metal-to-metal contact in the bearings under those heavy loads.
And surprisingly, oil also plays a major role in keeping things cool, doesn't it?
It does, a huge role. As oil circulates, it absorbs a significant amount of heat, particularly from crucial components like pistons and cylinder walls.
Wow.
In some reciprocating engines, oil cooling can actually handle up to 50% half of the total engine heat.
That's remarkable.
With a very effective way of transferring heat away to be dissipated by the oil cooler.
Okay, what else is oil doing inside the engine? It's quite the multitasker.
It also helps create a critical seal between the piston and the cylinder wall.
Ah, like stopping leaks.
Exactly. This prevents those high-pressure combustion gases from leaking past the piston rings. If they did, you'd lose power and efficiency. It's like a dynamic gasket, constantly reforming.
So it's sealing, it's cooling, and I know it also has a cleaning function.
Exactly. As oil flows through the engine, it picks up tiny foreign particles where debris, byproducts of combustion, dirt, all sorts of things.
Gunk, basically.
Pretty much. And it carries them to the oil filter, where they can be removed. This prevents abrasive wear that could damage engine parts.
And I heard about dispersants.
Yes. Many oils contain additives called dispersants. They help keep these particles suspended in the oil, making it easier for the filter to trap them, rather than letting them settle out somewhere inconvenient.
And it even helps prevent rust, which seems like a constant battle with metal parts.
That's right. When the engine is shut down, the oil leaves a protective coating on internal surfaces, shielding them from corrosion caused by moisture and other elements.
Okay.
This is why our source points out that infrequent engine shutdowns are actually better than letting an engine sit completely unused for extended periods.
Because that protective oil film can degrade over time.
Exactly. You want to keep things coated.
Okay, so we know what oil does, but what makes a particular oil the right choice for an aircraft engine? It can't just be any old oil, can it?
Definitely not. There are several key characteristics. First and foremost is viscosity.
Viscosity, that's like how thick or thin it is, right? Its resistance to flow.
Precisely. And this is where temperature throws a curveball.
Yeah, I can imagine.
Early oils could become almost solid, like molasses, in freezing conditions, making it nearly impossible to start the engine and get proper oil flow.
Right. No lubrication on startup. Bad news.
Very bad news. On the other hand, at high operating temperatures, some oils would become so thin, almost like water, that the vital protective oil film would break down, leading to rapid wear. Metal on metal again.
So you need an oil that can handle both extremes, not too thick when cold, not too thin when hot.
Exactly. It needs to be fluid enough to circulate when it's cold, but still maintain its protective film strength and ability to carry loads when the engine is hot.
And that's where the oil grade comes in, the SAE rating.
That's a big part of it. Using the correct oil grade specified by its SAE rating for a particular engine and its operating environment is absolutely essential.
Now, I've seen those numbers and letters on oil containers. In commercial aviation, what do those designations actually tell us, like grade 80 or 100?
Right. In commercial aviation, oils are often classified with numbers like 80, 100, or 140. These numbers roughly indicate their viscosity as measured by a standardized test.
The Sable Universal Viscosimeter. Quite a mouthful.
It is. Essentially, it's a way to measure how long it takes a specific amount of oil to flow through a calibrated opening at a precise temperature. Higher number, thicker oil. Simple as that.
Okay. And then there's the SAE system from the Society of Automotive Engineers, like SAE 30, SAE 50.
Yes, the SAE system groups oils, like SAE 10 up to 70, based on their viscosity at specific temperatures, usually 130 degrees APR or 210 degrees Fahrenheit.
So it's just a different scale?
Kind of. It's worth noting that these SAE ratings are somewhat arbitrary and don't directly correlate with the Sable numbers or, other grading systems. It's its own thing.
And what about that W I sometimes see, like SAE 20W50?
The W. That W after the number, like in 20W50, indicates that the oil meets specific viscosity requirements at lower temperatures, making it suitable for winter or cold weather use. This is different from a W before the grade number, such as W100. That W signifies that the oil is an ashless dispersant type.
Right, the cleaning stuff we talked about. It can be a bit confusing to keep track of.
You can, yeah.
So an SAE number just tells you how the oil flows at a certain temperature. It doesn't tell you if it's a top quality oil or not.
That's absolutely correct. An SAE rating is simply a viscosity grade. You can have both excellent and, less effective oils that happen to have the same viscosity at a given temperature and therefore fall into the same SAE category.
So the number isn't a quality mark?
Nope. The SAE letters themselves aren't a mark of overall quality. Our sources show how these commercial aviation grades, SAE numbers, and even older military specifications sometimes overlap or correlate, but viscosity is just one piece of the puzzle.
Okay, so viscosity is crucial, but you also mentioned something called the viscosity index. What's that all about?
The viscosity index, or it's 6. It's a number that tells us how stable an oil's viscosity is across a range of temperatures.
Stability. Yeah, okay.
Think of it like this. A low viscosity index means the oil's thickness changes dramatically. With temperature, it gets really thin when hot and really thick when cold, like a chameleon.
And a high viscosity index is what you're looking for.
Absolutely. An oil with a high viscosity experiences much smaller changes in viscosity over a wide temperature range.
So it stays more consistent.
Exactly. Ideally, you want an oil that stays relatively consistent. That ensures good flow when cold, for easier starting and quick lubrication, and sufficient thickness when hot to provide that essential protective oil film for the bearings.
Got it. There are also terms like flash point and fire point. Those sound pretty important for something operating inside a hot engine.
They are indeed very important. The flash point is the temperature at which the oil starts to release flammable vapors that will briefly ignite flash if exposed to a flame.
Just a quick flash.
Right. The fire point is a slightly higher temperature where enough vapors are produced to sustain a continuous fire.
Okay, definitely don't want that.
No. These are important safety indicators, showing the oil's ability to withstand the high temperatures within the engine without, catching fire.
And cloud point and pour point. Those sound like they relate to how well the oil behaves in cold weather again.
Correct. The cloud point is the temperature at which wax, which is naturally present in mineral oils, starts to solidify and form tiny crystals, making the oil look cloudy.
Hazy, yeah.
And the pour point is the lowest temperature at which the oil will still flow or can be poured. So if your pour point is, say, minus 30 degrees, it should still flow at that temperature.
Crucial for cold starts.
Absolutely. These are critical for determining if an oil is suitable for operation in cold environments.
Finally, specific gravity. Is that simply a measure of how heavy the oil is compared to water?
Essentially, yes. It's the ratio of the oil's density to the density of water at a specific temperature. For example, water weighs about 8.3 pounds per gallon. If an oil has a specific gravity of 0.9, that oil would weigh around 7.5 pounds per gallon.
So just another characteristic.
Exactly. Another way to characterize the oil's properties.
Now, thinking about the history of engine oils, it sounds like we've made significant progress from the early days of aviation.
We certainly have. Huge progress. In the early days of piston aviation engines, simple, straight mineral oils derived from carefully selected petroleum-based stocks were often adequate.
Like the grades 65, 80, on.
Exactly. Grades like 65, 80, 100, 120 were common. These were primarily high-viscosity index-based oils with very few additives, mainly just a poor point depressant to help with cold flow and maybe an antioxidant.
And these are still used for break-in.
Interestingly, yes. They're still the go-to for the initial break-in period of new or recently overhauled engines to help the piston rings seat properly.
But as engines became more powerful and operated under harsher conditions, hotter conditions, these basic oils weren't sufficient anymore.
Exactly. There was a growing need for improved resistance to heat and oxidation. The oil was breaking down too quickly.
So additives came into play.
Right. This led to the introduction of additives, initially metallic salts of barium and calcium. While these did improve stability, they had a significant downside.
There's always a catch.
There often is. They could leave ash deposits in the combustion chamber when they burned, which wasn't great for engine performance or longevity.
So how did they overcome that issue?
That's when ashless, non-metallic polymeric additives were developed. These are used in what we now know as W oils like W100.
The ashless dispersant oils.
Exactly. They solve the deposit problem and also have the added benefit of helping to stabilize the oil's viscosity across a wider range of temperatures, making it more consistent. They have better dispersancy, too, keeping those particles suspended.
And that eventually led to the development of multigrade oils, like the 15W50 we mentioned.
Precisely. Semi-synthetic multigrade oils like SAE W15W50 and those aviation-specific ashless dispersant oils like W80, W100, W120 were created. These combine high-viscosity index-base oils with sophisticated non-metallic additive packages.
Yeah, additive packages, right.
To enhance stability, dispersancy, that ability to keep particles suspended, and resistance to foaming. Foaming is bad because air bubbles don't lubricate well.
You mentioned semi-synthetic oils. What's the reason for blending synthetic and mineral oils? Why not just go full synthetic?
That's a good question. In some multigrade oils, a blend is used, partly out of concern that fully synthetic oil might not be the best at keeping lead deposits in suspension.
From the leaded aviation fuel.
Exactly. Lead byproducts are a reality in many piston engines. This semi-synthetic approach aims to provide the performance benefits of multigrade oils, the wide temperature range, while still effectively managing those lead byproducts.
And the major advantage of multigrade oils over the older monograde oils is that they can operate effectively across a much broader range of temperatures, right? That seems like the key benefit.
Absolutely. That's the headline. Multigrade oils offer better protection during cold starts because they flow more easily when cold.
Less wear during startup.
Right. And they maintain a stronger protective film, a higher effective viscosity at typical operating temperatures compared to a straight-weight oil that might be good for starting but too thin when hot.
And startup wear is significant.
Our source even notes that the initial engine start can cause a significant portion of normal engine wear due to that brief period of inadequate lubrication. So improved cold flow is a substantial benefit.
So for modern aircraft, especially those that fly in places with wide temperature variations or anything with a turbocharger?
Oh, especially turbocharged engines.
Ashless dispersant multigrade oils are generally the preferred choice.
Generally, yes. They offer the best all-around protection. But it's important to remember that regardless of the type of oil used, preheating the engine and the oil supply, when temperatures drop below about 20 degrees AREV or -7 degrees C, is still highly recommended.
Good practice anyway.
Always good practice. It minimizes wear and ensures proper lubrication right from the moment of startup.
What about when you have a brand new engine or one that's just been completely overhauled? Is there a specific type of oil that's recommended for that initial period?
Yeah, it's a bit different. Manufacturers often use a special preservative lubricating oil to protect new engines from rust and corrosion during storage and shipping.
Okay.
This oil typically needs to be drained after the first, say, 25 hours of operation. When adding oil during this initial break-in period, the recommendation is usually to use either aviation-grade, straight mineral oil,
The old school stuff.
right, to help those rings see properly, or sometimes an axis dispersant oil, but you really have to check the manufacturer's specific instructions for that engine. They dictate the break-in procedure.
And I recall reading that using ashless dispersant oil too early in new engines can sometimes lead to higher oil consumption. Is that right?
Yes, that can occasionally happen.
Yeah.
The very additives that are so good later on, the dispersants and friction modifiers in some ashless dispersant oils, can actually slow down the proper seating or break-in of the piston rings against the cylinder walls.
So they don't seal as well initially.
Exactly. In such cases, using mineral oil initially, maybe for the first 50 hours or until oil consumption stabilizes, and then switching to ashless dispersant oil is often the recommended procedure. The same principle applies if you've just replaced one or more cylinders.
It really sounds like the most important advice, again and again, is to always consult the engine manufacturer's recommendations.
Absolutely. Can't stress that enough. Their information, the pilot's operating handbook, the maintenance manuals is the definitive guide. Always follow that for selecting the correct oil type and adhering to the proper service intervals for your specific engine.
Okay, so we've covered a lot about the oil itself. Now, how does it actually circulate throughout the engine? I know there are different types of lubrication systems.
That's right. For reciprocating engines, the two primary classifications are wet sump and dry sump systems.
Wet sump and dry sump.
The key difference, as their names suggest, is where the main volume of oil is stored. A wet sump system holds the oil in a reservoir that's an integral part of the engine, typically the bottom of the crankcase, the oil pan.
So it's all contained within the engine block.
Pretty much.
Yeah.
After circulating, the oil simply drains back down into this internal reservoir.
And a dry sump system works differently.
Yes. In a dry sump system, the oil that drains to the bottom of the engine is pumped out of the engine's crankcase by what's called a scavenge pump.
Okay.
And sent to a separate external tank, which serves as the main oil storage reservoir.
So it needs extra pumps and lines.
Exactly. This system requires additional components. The scavenge pump, external lines to connect everything, and the dedicated oil tank. It's more complex.
So the dry sump system seems more complex. What are the advantages of using it? Why bother?
Well, several reasons. First, it allows for a larger oil capacity that might easily fit in the crankcase. Second, it ensures a constant supply of oil to the pump inlet, even during unusual flight attitudes, like climbs, dives, or turns, where oil in a wet sump might slosh away from the pickup.
Ah, like an aerobatic aircraft?
Definitely used there, but also on larger engines in multi-engine aircraft where reliability and cooling are paramount. It also allows the engine profile to be shallower, as you don't need a deep oil pan.
Makes sense. And because the dry sump system includes all the components of a wet sump system, plus these additional elements, it's often used as the primary example to understand how these systems function.
That's right. If you understand a dry sump, you pretty much understand a wet sump too, just minus the external tank and scavenge pumps.
And how is the oil actually delivered to all those moving parts? Is it just splashing around in there?
While some splash lubrication might occur, particularly hitting the cylinder walls from the rotating crankshaft, the main method in aircraft engines is pressure lubrication. You might sometimes see a combination of pressure and splash, especially in simpler engines, but pure splash lubrication, like in an old lawnmower, is never used as the sole method in certified aircraft engines. It's just not reliable enough.
What are the benefits of using pressure lubrication? Why is it the standard?
There are several key advantages. First, it ensures a consistent and reliable supply of oil, under pressure, to all the critical bearings and surfaces. No guesswork.
Positive delivery.
Exactly. Second, the large volume of oil that can be circulated under pressure provides a significant cooling effect, carrying heat away from hot spots.
We talked about that oil cooling function.
Right. And third, it guarantees proper lubrication regardless of the aircraft's orientation during flight, which is crucial, as we mentioned.
That makes perfect sense, especially during maneuvers or turbulence. Now, what are some general requirements that any aircraft engine lubrication system needs to meet, regardless of type?
Well, fundamentally, the system must operate effectively across all expected flight attitudes. climbs, dives, turns, level flight, and under all atmospheric conditions the aircraft is certified for.
Okay.
For wet sump engines, specifically, this requirement must be met even when the oil level is as low as half of the maximum usable capacity.
So safety margin there.
Definitely. All systems also need to be designed to facilitate oil cooling, either inherently or with a dedicated cooler. And the engine crankcase must be vented to the atmosphere.
Why the venting?
To prevent pressure buildup inside the crankcase from blow-by gases getting past the piston rings. If pressure built up, it could force oil out past seals and gaskets, causing leaks.
Okay, got it. Let's delve deeper into that dry sump system you mentioned. What are the main components we'd find in one? Walk us through it.
Okay, the principal components typically include the oil supply tank, the external one, the engine-driven pressure oil pump, one or more scavenge pumps, often more capacity than the pressure pump, and oil cooler.
To get rid of the heat?
Right, usually with some kind of control valve to regulate its operation. The oil tank vent lines we just talked about, all the necessary connecting tubing and hoses, and of course, instruments in the cockpit pressure and temperature gauges.
Yeah.
Our sources have good diagrams showing how it all fits together.
Let's start with the oil tank itself. I imagine it's not just a simple can.
Absolutely not. They're typically made of aluminum alloy, lightweight, but strong, and they must be able to withstand significant vibration and the forces from the fluid sloshing around inside during flight.
Okay.
Each tank must have an expansion space built in. This is crucial. It needs to be the greater of 10% of the tank's total capacity, or half a gallon.
Why so much expansion space?
2 reasons. Oil expands when it gets hot, and also the returning oil from the scavenge pumps can be quite foamy, full of air bubbles, which takes up more volume.
Yeah.
You need space for that.
Makes sense. And the filler cap needs to be pretty secure, I would think.
Definitely. It has to provide an oil-tight seal and is always clearly marked OLL. Pretty obvious, but important. There's usually a scupper or drain around the filler neck to handle any spills during filling.
And the vents?
Right, we mentioned vent lines. They're crucial for proper tank ventilation in all flight attitudes, often connected back to the engine crankcase. This prevents pressure differences and potential oil loss overboard through the vent. The tank is typically positioned close to the engine and high enough to ensure gravity helps feed oil down to the oil pump inlet.
In terms of capacity, how much oil do these tanks usually hold? Gallons?
It varies hugely depending on the aircraft and engine size, from a few quarts on smaller engines to many gallons on large transport aircraft. Generally, it's enough to provide an adequate supply for the entire expected duration of flight, based on the fuel capacity and expected oil consumption.
And inside the tank? Anything special?
Yeah, you'll often find baffles, internal plates designed to break up the swirling motion of the returning oil. This helps to minimize foaming before the oil gets drawn back into the pressure pump. Foamy oil doesn't lubricate well.
Right. Air bubbles don't protect bearings.
Exactly. Older radial engines sometimes use what's called a hopper tank, which had a smaller internal compartment or well. This meant only a portion of the total oil volume was circulating initially, helping it warm up more quickly on startup in cold weather.
Clever. How do pilots know how much oil is in the tank? Just a dipstick.
Most aircraft use a dipstick-type gauge, often called a bayonet gauge. Simple and reliable. Some larger aircraft have more sophisticated in-flight indicating systems that use a float mechanism and an electrical transmitter to display the oil quantity directly on the flight deck instruments.
And at the very bottom of the tank.
Usually a sump, a lower section designed to trap any moisture that condenses or sediment that might accumulate over time. There's always a drain valve there to allow for draining the tank and removing this gunk during maintenance.
Okay, next up is the oil pump. The heart of the system, pushing that oil around.
It really is. As oil leaves the tank and enters the engine system, it's pressurized by an engine-driven pump, almost always a gear-type pump.
Gear type, how does that work?
It's a positive displacement pump. It uses 2 closely meshed gears rotating within a tightly sealed housing. As the gears turn, they unmesh on the inlet side, creating a low-pressure area that draws oil in. The oil gets trapped in the spaces between the gear teeth and the housing,
Right.
carried around the outside of gears, and then forced out through the pressure port on the outlet side as the gears mesh back together. It's simple, robust, and delivers a pretty constant flow per revolution.
And one gear drives the other.
Yes, one gear is driven by a shaft connected to an accessory drive gearbox on the engine. Seals are obviously critical around that drive shaft to prevent leaks.
And right after the pump, the oil goes through a filter, I assume, to catch any contaminants before it gets to the engine bearings.
Absolutely essential step. The pressurized oil flows directly to the oil filter or sometimes a screen first to remove any solid particles that might be suspended in it. You don't want grit getting into those precision bearings.
And you mentioned a check valve sometimes, especially in radial engines.
Yes, in dry sump radial engines, where the tank is mounted high, there's often an oil filter check valve. This prevents gravity from slowly feeding oil down from the tank through the pump and into the lower cylinders when the engine isn't running.
Why is that bad?
If enough oil accumulated in a lower cylinder, it could cause a hydraulic lock or liquid lock when you try to start the engine. Liquids don't compress, so turning the engine over could bend or break a connecting rod. Very damaging. The check valve stops that slow seepage.
Smart. And what happens if the main filter gets clogged? You don't want to cut off the oil supply entirely. That sounds worse.
Exactly. That's where the oil filter bypass valve comes in. It's usually built into the filter housing or the filter adapter. If the filter becomes blocked, maybe with contaminants or just very thick, cold oil during startup that can't easily pass through the filter element, the pressure before the filter will rise. When it reaches a certain differential pressure, this bypass valve will open.
Letting the oil go around the filter?
Precisely. It allows unfiltered oil to bypass the filter element and still flow to the engine's critical components. As our source points out, dirty oil is definitely better than no oil at all in an emergency.
Good failsafe. I know there are different types of oil filters used in aircraft. What are the common ones we see?
We see screen-type filters, which use a fine metal mesh. They often act as suction filters at the pump inlet or scavenge oil pickups to catch larger debris. The Cuno filter, which uses a stack of rotating discs and stationary cleaner blades to scrape off contaminants, is less common on modern light aircraft, but was used quite a bit previously.
Okay.
Then there are canister-type filters, which have a replaceable filter element housed within a metal canister that gets opened up for element changes.
Wow.
And probably the most widely used today for reciprocating engines are full-flow spin-on filters, much like on a car, but built to aviation standards.
Spin-on convenient.
Very. Full flow means that all the oil normally passes through the filter element before reaching the engine bearings. These spin-on filters often integrate the anti-drain back valve we mentioned to keep the filter full, and the pressure relief or bypass valve right into the disposable unit.
After the filter, is the oil pressure always constant, or does it vary?
Well, the pump output varies with engine speed, right? More RPM, more flow.
Yeah.
So the oil pressure needs to be regulated to ensure adequate lubrication without causing leaks or damaging components due to excessive pressure.
Ah, okay. So something controls it.
Exactly. That's the role of the oil pressure regulating valve, sometimes just called a relief valve, though its primary function here is regulation. It limits the pressure in the main supply line to a predetermined value.
How does it do that?
It's typically a spring-loaded valve. When the oil pressure going to the engine exceeds the spring tension, the valve opens and diverts the excess oil flow back to the inlet side of the pressure pump.
So it just bleeds off the extra pressure.
Exactly. This pressure setting is usually adjustable, maybe with a screw, or by adding or removing shim washers under the spring. But it's crucial to perform this adjustment only when the oil is at its normal operating temperature and the correct viscosity is confirmed, and always follow the manufacturer's specific procedures.
Right. And how does the pilot know what the oil pressure is doing? There must be a gauge.
Absolutely. The oil pressure gauge in the cockpit is a primary flight instrument. It displays the pressure of the oil as it leaves the pump and filter assembly and enters the engine's lubrication passages.
So it tells you the system is working.
Or if it isn't, it's a vital indicator that can provide an early warning of oil supply problems, pump failure, major bearing damage causing a pressure drop, or even ruptured lines.
What kind of mechanism is usually behind the gauge?
Many aircraft use a mechanical Borden tube mechanism. It's a curved, sealed tube that tries to straighten out as pressure inside increases, moving a needle on the gauge face through linkages. These often have a built-in restrictor fitting in the line to dampen the pressure pulsations coming from the pump, so the needle doesn't bounce around wildly.
Makes sense.
Multi-engine aircraft will obviously have individual pressure gauges for each engine. And the current trend, especially in newer aircraft, is towards using electrical pressure transmitters located on the engine, sending a signal to an indicator in the cockpit.
Why the move to electrical?
Lighter weight eliminates the need for long, potentially leaky, fluid-filled lines running all the way from the engine to the instrument panel.
Okay, we've discussed pressure. Now, what about oil temperature? That must also be an important parameter to monitor.
Absolutely critical. The oil temperature indicator allows the flight crew to monitor the temperature of the oil, which gives a good indication of the engine's internal temperatures and the cooling system's effectiveness.
Where is the temperature usually measured?
The location of the temperature sensor bulb can vary. In dry sump systems, it might be located in the inlet line to the oil cooler, measuring the hottest oil. In wet sump systems, it's often positioned after the oil cooler, measuring the temperature of the oil going into the engine. The key is it measures the temperature before the oil reaches the hottest internal parts of the engine, like the bearings.
And it connects to a gauge on the flight deck.
Yes, connected to a gauge, often similar electrically or mechanically to the pressure gauge system. It helps the pilot confirm the proper functioning of the oil cooling system and manage engine temperatures during different phases of flight.
So we have a pump, a filter, pressure regulation, and temperature monitoring. Now, how does the system actually cool the oil when it gets too hot?
That's the job of the oil cooler. It's essentially a heat exchanger. It can be cylindrical or elliptical in shape, containing a core made of many thin copper or aluminum tubes, often arranged in a honeycomb structure.
Honeycomb, okay.
Cooling air, either ram air or air directed by baffling, flows through these small tubes. The hot oil from the engine flows around the outside of these tubes through the spaces between them within the cooler's shell.
So the heat transfers from the oil to the air passing through?
Exactly. Heat transfers from the hot oil to the cooler metal of the tubes, and then to the air flowing through the tubes, which carries the heat away. Baffles inside the core sometimes help to direct the oil flow across the tubes multiple times for more efficient heat transfer.
And does the oil always go through the cooler? What if it's cold?
Good question. Some coolers also have a bypass passage or jacket built around the core. So if the oil is very cold and viscous during startup, or if the core were to become blocked, the oil can flow around the core to aid in quicker warm-up and prevent excessive pressure buildup.
And you need a way to control how much cooling takes place, right? You mentioned regulating it. You don't want to overcool the oil either.
Exactly. That's the function of the oil cooler flow control valve, often called a thermostatic bypass valve or vernotherm valve. Its job is to determine whether the oil needs cooling or not.
How does it know?
It usually contains a thermostatic element, often wax-filled or bimetallic, that expands or contracts based on the oil's temperature. When the oil is cold, the valve directs the majority of the oil flow through the bypass passage, straight back to the engine or tank, allowing it to warm up quickly.
Okay.
As the oil heats up, the thermostat expands, gradually closing off the bypass route and forcing more and more oil to flow through the cooler core where it can be cooled down, maintaining the desired operating temperature range.
Clever. I also came across something called surge protection valves in the materials. What are they protecting the system against? Surges of what?
Surges of pressure, specifically in the oil return line from the engine back to the tank, especially during cold starts.
What?
When the oil is very cold and thick, like syrup, the scavenge pump returning that thick oil to the tank can generate extremely high pressure in the return line, potentially high enough to damage the oil cooler core, which isn't always designed for super high pressure, or even burst hoses.
Ah, okay. So the surge valve prevents that.
Exactly. Surge protection valves are designed to relieve this potentially damaging high pressure. One common type is actually integrated into the oil cooler flow control valve itself, using spring-loaded valves that open if pressure gets too high. Others might be separate units installed directly in the return line, acting like a safety relief valve, just for the cooler circuit.
And how do you control the amount of airflow through the oil cooler to fine-tune the oil temperature? The thermostatic valve directs the oil, but what about the air?
Good point. Controlling the airflow through the cooler is the other main way to regulate oil temperature. There are a couple of primary methods used. Older aircraft, particularly those with radial engines, often use cowl flaps. These are adjustable panels at the rear of the engine cowling. By adjusting the opening of these flaps wider open or more closed, you control the amount of air exiting the cowling after passing over the engine cylinders and the oil cooler. More airflow equals more cooling.
Okay, so they affect both engine and oil cooling.
Often, yes. Another method involves a controllable flap or shutter located directly on the air exit duct of the oil cooler itself. This gives more precise control just over the oil cooling airflow. These controls can be either manually operated by the pilot via levers or cables, or electrically operated with a switch.
I also read about automatic oil temperature control systems. How do those work? Seems useful.
They are very useful, especially on more complex aircraft. The floating control thermostat is a common type of automatic system. It uses an electrically powered actuator, a small motor, and gearbox to adjust the position of the oil cooler air exit door or flap.
And what tells the actuator what to do?
It gets signals from a thermostat sensor positioned in the oil line, usually downstream of the cooler. This thermostat typically uses a temperature-sensitive element, maybe a bimetal strip or another type, that expands or contracts with temperature changes. This movement influences electrical contacts and tell the actuator motor which way to open the flap for more cooling if the oil is hot, or close it if the oil is getting too cool. It floats or hunts around the desired temperature set point. Newer systems often use more sophisticated electronic sensors and controllers, maybe integrated with the engine management system, but the fundamental principle of automatically regulating cooling airflow remains the same.
And what happens if an aircraft has two oil coolers? Does that happen?
Yes, some lubrication systems, especially on larger aircraft or high-performance engines, utilize dual oil coolers side by side or in series to provide increased cooling capacity.
How does that work?
Such systems often include a flow divider valve to split the oil flow evenly between the two coolers, potentially individual flow regulators or thermostatic valves for each cooler, and usually a mechanism to control both air exit doors together in response to the sensed oil temperature, ensuring balanced cooling between the two units.
Okay, that's a pretty comprehensive overview of the components in a dry sump system. Can you walk us through how it actually operates in practice? Let's take a typical small single-engine aircraft as an example.
Certainly. Let's imagine a common setup, maybe a 225 horsepower, 6-cylinder, horizontally opposed, air-cooled engine equipped with a dry sump system.
Okay, like in many Pipers or Moonies.
Exactly.
Yeah.
So oil is drawn from the external tank by the engine-driven pressure pump, usually through a coarse suction screen in the tank or line first, just to catch any large debris.
Right.
This pressurized oil then flows, typically, to the main full-flow filter assembly. This filter, as we said, has a bypass valve inside in case it gets clogged. Somewhere nearby, usually integrated with the pump or filter housing, is the pressure regulating valve, which maintains the desired system pressure by diverting any excess oil flow back to the pump's inlet side.
Okay, pressure set. Where next?
From there, the clean pressurized oil enters a main distribution manifold or gallery within the engine block. Drilled passages then carry this oil to all the engine's critical plane bearings. The crankshaft main bearings, the connecting rod bearings, the camshaft bearings, lifters, rocker arms, etc.
So direct pressure feed to the important spinning bits.
Absolutely. The cylinder walls, pistons, and piston pins are typically lubricated by oil that is sprayed or splashed out from the crankshaft and connecting rod bearings as they rotate. This spray lubrication can be less effective on very cold days before the oil warms up, which is another key reason why multi-viscosity oils are so beneficial. They flow better when cold.
Good point. So after the oil has done its job lubricating and cooling these components, where does it go?
It drains down by gravity into one or more sumps located at the bottom of the engine crankcase or accessory case. Now, the scavenge pumps kick in. There might be one or several, strategically located to pick up this oil from the sumps. Scavenge pumps are designed with a higher total pumping capacity than the pressure pump.
Why higher capacity?
Because the oil they're picking up is often mixed with air and blow-by gases, making it foamy and increasing its volume. They need extra capacity to handle this aerated oil and keep the crankcase effectively dry.
Gotcha.
These scavenge pumps then push the collected oil out of the engine and typically send it through the oil cooler.
Where the temperature gets managed.
Right, where that thermostatic bypass valve we discussed controls how much cooling occurs based on the oil temp. After the cooler, or bypassing it if cold, the oil is returned back to the top of the main supply tank, often through a de-aerator fitting to help remove air bubbles, ready to start the cycle all over again.
That's a clear picture. What about a wet sump system? How does its operation differ? Seems simpler.
It is simpler in its basic operation, yes. The main difference is storage. The oil is stored in the sump, which is essentially the enlarged lower part of the engine crankcase, acting as the oil pan or reservoir. Its capacity is limited by the size of this internal sump.
And you check the level with a dipstick going into the engine itself?
Usually, yes. A dipstick goes directly into the crankcase sump. There's typically a screen strainer at the oil pump pickup tube inlet within the sump to filter out any large particles before they reach the pump.
Okay.
An engine-driven pressure pump, similar to a dry sump one, then draws oil from the sump and circulates it under pressure, usually first through a filter mounted on the engine.
With a bypass valve?
Yes. usually incorporates a bypass valve. There's also a pressure relief or regulating valve, again, often built into the pump or filter adapter, to compensate for changes in pump speed and oil viscosity and maintain correct pressure.
And lubrication of parts.
Similar principle. The pressurized oil goes through internal passages to the crankshaft bearings, conrod bearings, camshaft, etc. The oil that is sprayed or flung off these pressure-lubricated components then lubricates the cylinders, pistons, and other parts before simply draining back down into the sump under gravity for recirculation.
Much simpler return path.
Much simpler. No scavenge pumps, no external tank or lines. The main drawback, as we mentioned, is that wet sump systems are generally not suitable for sustained inverted flight or extreme attitudes, as the oil pump pickup could become uncovered, starving the engine of oil.
Right, the oil would slosh to the top. Okay, so those are the systems in operation. What kind of maintenance is required to keep these lubrication systems functioning properly day to day or during inspections?
Maintenance involves a range of checks and procedures for various components. It's a critical part of any inspection.
Like the oil tank in a dry sump system.
Right. For the oil tank, it includes regular servicing, ensuring it's filled to the correct level. You need to check it carefully, often using a dipstick. And it's important not to overfill to leave that expansion space.
Good point.
You also check the security of the tank mounting straps, the condition of the filler cap seal, and the vent lines for obstructions or kinks. Periodically, the tank might need to be removed for inspection or repair, which involves careful draining, disconnecting lines, removing straps, and then meticulous reinstallation, ensuring all connections are properly tightened and safety wired if required.
What about the oil cooler? What do you check there?
For the common honeycomb type of cooler, you inspect the cooling fins for damage or blockage by dirt or debris, which would reduce efficiency. You check the mounting brackets for security and cracks, and you'd look for any signs of leaks around the fittings or seams. Operationally, you'd monitor the oil temperature in flight to ensure the thermostatic bypass valve is functioning correctly, warming up reasonably quickly, but not getting too hot under load.
And those oil screens and filters seem like they would require regular attention. They're catching all the junk.
Absolutely crucial. Both the pressure oil filter element and any suction or scavenge oil screens tend to accumulate sludge and wear particles over time. They need to be removed and inspected at specified intervals, often every 50 or 100 hours, or sooner, depending on the operation.
What are you looking for when you inspect them?
You're carefully examining the trapped debris for any contamination, but especially for those telltale metal particles, flakes, chips, or excessive fuzz that can indicate internal engine wear is occurring.
Like bearing material.
Exactly. Different metals point to different components. Finding small amounts might be normal, but significant amounts or specific types of particles warrant further investigation. After inspection, screens are thoroughly cleaned and filter elements are replaced. Always use new seals or gaskets and torque fittings correctly on reinstallation.
And the pressure relief valve.
The oil pressure relief regulating valve also requires periodic checks to make sure it's maintaining the system pressure within the manufacturer's specified range at normal operating RPM and temperature. Adjustments might be needed occasionally, following the precise instructions in the maintenance manual.
When it comes to actually changing the oil, are there any best practices to keep in mind beyond just draining and refilling?
Yes, regular draining and refilling are crucial, obviously, for removing accumulated contaminants, things like unburned fuel, moisture from condensation, acids formed during combustion, dirt ingested through the breather, carbon deposits, and those fine metallic wear particles we've discussed.
So it's not just about the oil wearing out, but getting dirty.
Primarily about getting dirty and contaminated. The specific intervals for oil changes vary depending on the aircraft, engine type of oil used, and how it's operated, but it's usually based on flight hours or calendar time, whichever comes first.
And you mentioned being careful when switching oil types.
Yes, particularly when transitioning from a long period of using straight mineral oil to an ashless dispersant AD oil. The AD oil is designed to clean, and it can loosen up old sludge deposits that were previously stable within the engine.
Which could then clog things up?
Potentially, yes. Clog oil passages or the filter. So the recommendation is usually to drain the mineral oil thoroughly, don't mix types if possible, and then run the engine for shorter intervals initially with the new AD oil, checking the screens and filters frequently, maybe after just 10 or 25 hours, until you're sure no excessive sludge is being dislodged.
Good tip. And turbocharged engines always need 80 oil.
Generally, yes, all turbocharged piston engines require ashless dispersant oil due to the higher operating temperatures involved.
And for new or overhauled engines?
Yeah. As we discussed, more frequent initial oil changes and screen filter cleanings are often recommended during the break-in period, maybe at 25 hours and 50 hours, to remove any manufacturing debris or initial wear particles. Again, follow the manufacturer's schedule. A common regular interval afterwards might be every 50 flight hours or every 4 months for an oil and filter change, with screen cleaning perhaps more often if only screens are fitted.
And when you remove the old oil filter, what should you be doing besides just throwing it away?
Inspecting the contents. This is a vital diagnostic step. For spin-on filters, you should carefully cut the metal can open using a specialized filter cutter tool.
Not a hacksaw.
Preferably not, as a hacksaw can introduce metal shavings that confuse the inspection. Once open, you unfold the pleated filter paper element and examine it closely under a good light.
Looking for those metal particles again?
Exactly. You're looking for any embedded metal particles, shiny flakes, aluminum bearing material, slivers, steel from gears or cams, brass or bronze bits, bushings, etc. You might use a magnet to differentiate ferrous iron steel particles from non-ferrous ones.
And finding metal is always bad.
Not necessarily always catastrophic. Tiny amounts of carbon or maybe a few minute flakes might be normal wear, but finding significant quantities, large pieces, or a sudden increase from previous inspections is a red flag indicating abnormal wear or a potential component failure starting. It requires investigation to pinpoint the source. This filter inspection is maybe the best window we have into the engine's internal health between overhauls.
Finally, are there any quick tips for troubleshooting common oil system problems if the pressure is low or temperature is high?
Our sources provide a helpful troubleshooting chart or guide. It lists common malfunctions like low pressure, high temperature, low temperature, excessive oil consumption, or foaming, and then suggests potential causes and remedies for each. Things like checking the oil level first, looking for leaks, checking gauge accuracy, inspecting the relief valve, ensuring the cooler isn't blocked, etc. It's a good starting point for diagnosing and addressing typical lubrication system troubles, but complex issues often require a qualified mechanic.
That's a really comprehensive look at reciprocating engine lubrication, incredibly important systems. Now, let's shift our focus to turbine engines. I understand that their lubricant requirements are quite different. They spin much faster, right?
They do. And the operating environment is very different, because turbine engines generally lack the high reciprocating loads found in piston engines and predominantly use ball and roller bearings, anti-friction bearings. They can operate effectively with much less viscous, thinner lubricants.
So not the thick stuff like SA50?
Generally not, no. However, these thinner turbine oils still need to possess exceptional properties. They need enough viscosity to carry the substantial loads on gears in the accessory drive section, but low viscosity to flow easily through small passages and provide cooling at the high altitudes and potentially low temperatures where they operate.
What else is crucial for turbine oils?
Low volatility is critical to prevent excessive evaporation at high temperatures and altitudes. They must resist foaming, which can be a bigger issue at high altitudes. They have to be compatible with the various synthetic rubber seals used throughout the engine. And, very importantly, they must minimize the formation of carbon and varnish deposits, often called coking, which can occur at the extremely high temperatures found in the turbine bearing areas.
And these are usually synthetic oils.
Almost exclusively synthetic oils in modern turbine engines. They're often supplied in sealed 1-quart cans to maintain absolute purity, as contamination can be a major problem.
What are the primary advantages of using synthetic oils in turbine engines compared to the older petroleum-based oils that might have been used decades ago?
The biggest advantage is their thermal and oxidative stability. They exhibit a much lower tendency to break down, evaporate, or form those harmful lacquer and coke deposits at the extremely high temperatures encountered in turbine bearing compartments compared to petroleum oils. They just handle the heat much better.
And they have additives, too.
Oh, yes. Turbine oils contain a complex blend of additives specifically designed to further enhance their thermal and oxidation stability, improve their load-carrying capacity for gears, lower their pour point for good cold weather starting performance, and provide other benefits like corrosion inhibition and anti-wear properties.
I noticed some military specifications mentioned in the source material, like MIL-L 7808 and MIL-PRF 23699F. What do those signify in the context of turbine oils?
Those are U.S. military specifications that have historically driven turbine oil development and are often used as benchmarks for commercial oils as well. MIL L7808 was an earlier specification, often referred to as Type 1, typically a lower viscosity oil. MIL PRF 23699F is a more modern and generally more stringent specification, often called Type 2. There's also a newer high thermal stability version, Type 2 HTS.
And these specs define performance.
Yes. These specifications define critical performance characteristics. Things like the oil's tendency to form deposits, both in liquid and vapor phases, its load-carrying ability under high stress for gears, overall engine cleanliness after use, its resistance to breaking down under high temperatures, bulk stability, its compatibility with other approved oils, though mixing different brands, even of the same spec, is generally not recommended by manufacturers.
Okay.
And importantly, their effect on engine seals. You don't want the oil degrading the seals and causing leaks. Meeting these specs ensures a certain level of performance and quality.
Turbine oils sound highly specialized and maybe a bit aggressive chemically. Are there any particular safety precautions to keep in mind when handling them?
Yes, while they generally present a low health risk under normal operating conditions with standard industrial hygiene, some precautions are wise. Prolonged or repeated contact with the liquid vapors or mists should be minimized.
So wear gloves.
Good practice, yes. Ingestion should obviously be avoided entirely. Skin contact can cause irritation in some individuals. Eye contact should also be avoided. Safety glasses are a good idea.
What about fumes?
Importantly, at very high temperatures, well above normal operation, turbine oil can thermally break down and produce potentially toxic byproducts, so caution is warranted if dealing with extreme overheating situations or fires. Also, they can be quite damaging to paint, so any spills on the aircraft exterior should be cleaned up promptly using an appropriate petroleum-based solvent.
Good to know. Now, I've heard about a program called SOAP Spectrometric Oil Analysis Program. Is that mainly for turbines or used for piston engines too?
It's a very valuable preventative maintenance tool used extensively for both turbine and reciprocating engines, actually.
How does it work?
It involves taking regular small samples of the engine oil and sending them to a specialized lab for analysis using a spectrometer. This instrument analyzes the oil for minute traces of various metallic elements measured in parts per million ppm.
Metals. Where do they come from?
They come from the engine's internal components wearing down over time. Because the oil circulates everywhere, it picks up microscopic particles of these wear metals, iron from cylinders or gears, chromium from rings, aluminum from pistons or cases, copper from bushings, silver from bearings, etc.
So you're looking for signs of wear?
Exactly. By identifying which metallic elements are present and precisely measuring their concentration in ppm, specialists can gain valuable insights into the engine's internal condition. It's like a blood test for the engine.
And what tells you there's a problem?
It's usually about trends. A sudden increase in the concentration of a particular metal or a level exceeding established limits for that engine type can be an early warning sign of abnormal wear occurring in a specific component or system. For example, a spike in silver might point to bearing distress.
So it's like getting a detailed warning before something breaks.
That's the whole point. By regularly monitoring the levels of different wear metals and comparing them to historical data for that specific engine and established norms, maintenance personnel can detect abnormal wear rates and potentially address issues weeks or even months before they might otherwise be discovered through routine inspections or, worse, an in-flight failure.
That sounds incredibly useful for safety and maintenance costs.
Absolutely. This proactive approach significantly increases safety and can lead to substantial cost savings by allowing for timely intervention, maybe replacing a specific bearing or gear before more extensive catastrophic damage occurs. Our source lists many of the typical wear metals found and indicates which engine components their presence might point to. It's a really powerful diagnostic tool.
Okay, now let's look at the turbine engine lubrication systems themselves. Are they all dry sump systems, like the reciprocating examples we focused on earlier? Or are there wet sump turbines too?
Both wet sump and dry sump systems are utilized in gas turbine engines, although dry sump systems are probably more common, especially on larger engines.
Same principle. Wet sump oil stored internally. Dry sump uses an external tank.
Exactly the same basic principle regarding oil storage. Wet sump systems store the oil within the engine structure itself, often in the accessory gearbox or a dedicated sump. Dry sump systems employ that separate external oil tank.
And how are they categorized besides wet-dry?
Turbine oil systems can also be categorized by their method of pressure regulation. You have pressure relief systems, which use a valve to maintain a relatively constant pressure downstream, similar to many piston engines. Then you have full flow systems where the oil pressure delivered to the bearings actually varies somewhat proportionally with engine speed. There's still a relief valve for overpressure protection, but not constant regulation. And finally, total loss systems, which are very rare, used for short-duration applications like missiles, where the oil is just sprayed once and not recirculated.
Which is most common on airliners.
The pressure relief system, often combined with full-flow filtration, is probably the most common type found on large turbofan engines powering commercial aircraft.
And the primary function of the oil in a turbine engine, is it still mostly lubrication, or is cooling more dominant?
That's a great question. While effective lubrication of bearings and gears remains crucial, cooling the engine's bearings is often considered equally, if not more, critical in turbines due to the extremely high rotational speeds and the intense heat generated, especially in the turbine section.
So the oil is really working hard as a coolant.
Tremendously hard. The oil circulates through the bearing compartments, absorbing and carrying away the immense heat generated by friction and conducted from the hot gas path. The exhaust turbine bearings are particularly critical due to the intense heat back there, near the combustion gases. These often utilize supplementary air cooling in addition to oil cooling.
Air cooling, too. Where does that air come from?
This secondary airflow is typically cooler air bled from earlier stages of the engine's compressor. This bleed air is carefully ducted, not only to help cool bearings, but also to cool other hot components like the turbine discs, vanes, and blades themselves. This extensive use of internal air cooling actually helps to reduce the total heat load that the oil system has to manage.
So the air and oil work together on cooling?
Very much so. And then, of course, you still need dedicated oil coolers, which can be air-cooled using ambient or fan bypass air, or fuel-cooled using the aircraft's fuel as a cooling medium, or often a combination of both are essential for regulating the bulk oil temperature back down before it recirculates.
Fuel-cooled? That seems counterintuitive. Isn't the fuel flammable?
It is, but the heat exchangers are designed very carefully. Using fuel to cool the oil has a neat side benefit. It also heats up the fuel.
Ah, which helps prevent ice crystals forming in the fuel, right? Especially at high altitudes.
Exactly. It serves a dual purpose, cooling the oil and warming the fuel to prevent fuel system icing. Very efficient design.
What are the key components we would typically find in a turbine engine lubrication system? It sounds complex.
The specific components and their arrangement can vary a lot between engine models, but you'll generally find these core elements in most dry sump systems. The oil tank, obviously external. The oil pump, which is often a multi-element unit containing both the pressure supply stages and multiple scavenge pump stages, all in one housing.
Multiple scavenge stages. Why?
Because you need to scavenge oil efficiently from several different bearing compartments and the accessory gearbox simultaneously.
Makes sense. What else?
Oil filters absolutely critical due to the high speeds and tight tolerances. Turbines often use finer filtration than piston engines. There will be a main pressure filter, often with differential pressure indicators or bypass warnings, maybe secondary screens for scavenged oil, and often tiny last chance filters right at the oil spray nozzles for the bearings.
Last chance filters.
Yep, tiny little screens right before the oil sprays onto the bearing, just in case any debris got past the main filter to protect those critical bearing elements.
Okay, then pressure regulation.
An oil pressure regulating valve in pressure-regulated systems, or an oil pressure relief valve for overpressure protection in variable pressure systems. You'll find the oil jets or nozzles themselves designed to spray or sometimes mist lubricant precisely onto the bearings and gears.
How is everything monitored?
Lots of instrumentation connections for pressure sensors, temperature bulbs, oil quantity transmitters, maybe low-pressure warning switches, filter differential pressure sensors, often feeding data to the cockpit displays like ICAS or ECAM.
What about venting? Still needed.
Definitely. Breather systems are crucial to vent excess air and fumes from the bearing compartments in the oil tank, maintaining proper internal pressures and preventing leaks. They often lead to a doiler or air oil separator.
Doiler?
Yes, a device often using centrifugal force that spins the oil mist out of the vented air before the air is discharged overboard, minimizing oil loss.
Clever. Anything else?
Check valves are important to prevent oil from seeping down into lower bearing compartments or the accessory gearbox after shutdown, which could cause issues on the next start. Thermostatic bypass valves, just like in piston engines, to control flow through the oil coolers. The oil coolers themselves, air oil and door fuel oil. And very commonly, magnetic chip detectors.
Ah, like the SOAP program, but catching particles directly.
Exactly. These are magnetic plugs placed strategically in the scavenge lines or sumps. They attract and hold any ferrous, iron or steel particles circulating in the oil. They're checked regularly during maintenance, and finding metal chips provides a direct, immediate indication of potential component distress, often complementing the SAP analysis.
That's quite a comprehensive list. Let's take a look at an example. A typical dry sump, pressure-regulated turbine lubrication system, like you said, is common on airliners. How does that generally operate?
Okay, such a system typically consists of three main interconnected subsystems: the pressure subsystem, the scavenge subsystem, and the breather subsystem.
Pressure first.
The pressure subsystem uses a gear-type pump, or sometimes a gerotor pump, to draw oil from the external tank. It pushes this oil under pressure through the main filter assembly, which includes the bypass valve. The pressure is controlled by the regulating valve, which spills excess back to the pump inlet.
Okay.
The regulated filtered oil then typically flows through the fuel oil heat exchanger, maybe an air oil cooler as well, depending on the temperature, and is finally delivered through a network of tubing to the engine's main bearings, compressor and turbine, and the accessory drive gearbox. Last chance filters and precisely aimed spray nozzles ensure lubrication right where it's needed.
Then the scavenge system collects it.
Right. The scavenge subsystem employs multiple scavenge pump elements, often housed with the pressure pump. These elements collect the used, hot oil from the various bearing compartments, which are sealed, and the accessory gearbox sump. They pump this oil, which is usually mixed with air, back towards the oil tank.
Does it go through the cooler on the way back?
Sometimes the cooler is in the scavenge return line, sometimes in the pressure line after the pump designs vary. The scavenged oil usually passes through a deaerator device in the tank to remove the entrained air before it becomes supply oil again. Chip detectors are typically located in the scavenge lines from each major area.
And the breather system?
The breather system connects the air spaces in the sealed bearing compartments and the oil tank vent together, usually routing the air-oil mist mixture to that central doiler, often located in the accessory gearbox. The doiler separates the oil, which drains back into the gearbox, from the air, and the relatively clean air is then vented overboard through a breather outlet. This ensures all compartments operate at roughly the same pressure, preventing unwanted oil flow between them.
Okay, I think I follow that. And what about a dry sump system where the oil pressure isn't strictly regulated by a bypass valve, the variable pressure type? How does that differ?
In a dry sump variable pressure lubrication system, the fundamental subsystems are very similar: pressure, scavenge, breather. The key difference is in the pressure subsystem. The main oil pump's discharge pressure is not actively regulated down to a constant value by a bypass valve recycling flow back to the inlet.
So the pressure changes with engine speed?
Essentially, yes. The pump's output pressure is designed to be roughly proportional to the engine's rotational speed, RPM. So higher RPM means higher oil pressure, up to a point. There's still a main pressure relief valve in the system, but it only opens as a safety measure if the pressure exceeds the absolute maximum design limit, perhaps during a cold start or an overspeed condition. It doesn't continuously regulate pressure during normal operation.
Where does the oil go then?
The pressurized oil still flows through the filters with bypass, through the coolers, air oil and/or fuel oil controlled by thermostats, and then via last chance filters and nozzles to the bearings, gearboxes, and seals. The scavenger and breather subsystems function pretty much the same way as in the pressure-regulated system, collecting oil, detecting chips, degrading, and venting air overboard.
Turbine engines also utilize wet sump lubrication systems, although they sound less common, maybe on smaller turbines. How do those typically operate?
They are indeed less common on larger engines, but are used particularly on smaller turboprops, turboshafts, or APUs, auxiliary power units. In a turbine engine wet sump system, the oil reservoir is an integral part of the engine's structure, as we said.
Part of the gearbox, usually?
Often integrated into the accessory gear case or a dedicated sump area that forms the bottom of the engine structure. The reservoir itself is usually equipped with components like a sight gauge or dipstick to check the oil level, a vent breather connection, a magnetic drain plug, and provisions for installing temperature and pressure sensors.
How are the bearings lubricated?
It can be a mix. The engine's main bearings, like compressor or turbine shaft bearings, might still be pressure-fed by a pump drawing oil from the sump through a filter and delivered via nozzles. However, the accessory drive gears and some other components might be lubricated primarily by splash or submersion as they rotate within the oil held in the sump gearbox. Used oil then simply drains back down into the integral reservoir by gravity, much simpler plumbing than a dry sump.
Finally, what does the routine maintenance of turbine engine oil systems typically involve, similar to piston engines?
Broadly similar categories of tasks, but the specifics and intervals can be quite different and often more stringent due to the operating conditions. Maintenance encompasses tasks like adjusting pressures, removing, cleaning, and replacing various components like filters and chip detectors.
Filter changes are critical.
Absolutely. Oil filter maintenance and oil change intervals are highly dependent on the specific engine model, the type of oil used, some have very long life, and the operating environment. Following the manufacturer's maintenance manual and approved schedule is essential. Typical filter maintenance involves carefully removing the filter bowl or housing, removing the element, inspecting it closely for debris, similar to piston filters looking for metal, cleaning the housing, installing a new element and seals, and torquing correctly.
What else gets checked regularly?
Oil pressure adjustments might be needed occasionally on the regulating or relief valves. Regularly checking the oil level is critical, usually done shortly after engine shutdown for turbines, while the oil is still warm and hasn't all drained back, using a dipstick or a sight gauge. The scavenge and breather systems need inspection for leaks, security of lines and fittings, and of course, regular inspection and cleaning of magnetic chip detectors and any accessible last chance filters. SOP analysis is usually a routine part of the monitoring program, too.
That provides an incredibly detailed look at lubrication for both major engine types. Hugely important stuff. Now, let's move on to the other vital aspect needed to keep these engines running. Engine cooling systems. We've touched on oil cooling quite a bit, but what about the overall cooling of the engine structure itself?
Yes, managing heat is a constant and absolutely critical challenge in both reciprocating and turbine engines. As we've hinted, excessive heat is always undesirable. It can lead to detonation in piston engines, weakened components, lubrication breakdown, and ultimately significant damage or even catastrophic failure.
How are they generally cooled? Different approaches.
Very different approaches for the two main types. The vast majority of reciprocating aircraft engines are air-cooled. Some more recent aircraft diesel engine designs, however, do utilize liquid cooling systems, similar to a car where a coolant fluid like glycol and water mix is circulated through jackets surrounding the cylinders, and the absorbed heat is then dissipated to the outside air by a radiator.
But most Cessnas, Pipers, etc. are air-cooled.
The vast majority, yes. Turbine engines, in contrast, primarily rely on carefully managed internal airflow, using air bled from the compressor for both internal component cooling and some external cooling, supplemented by the oil system.
Let's focus on reciprocating engines first. I know those prominent fins on the cylinders are the most obvious part of the cooling system, but it sounds like there's more to it than just fins.
Absolutely. An internal combustion engine is fundamentally a heat-generating machine. A surprisingly large portion, maybe 2/3 or more, of the energy released from burning fuel is not converted into useful power, but ends up as waste heat.
Wow, that inefficient.
In terms of turning heat into work, yes. If this waste heat isn't effectively removed, it causes major problems. We mentioned pre-ignition or detonation, uncontrolled combustion, weakening of metal parts like pistons and cylinders due to overheating, and breakdown of the lubricating oil film.
How much heat are we talking about?
Tremendous amounts. Our source gives an example. 1 gallon of aviation gasoline contains enough heat energy to boil about 75 gallons of water. That's a lot of heat being released inside those cylinders.
So where does it all go?
About half, maybe a bit less, is carried away out the exhaust pipe with the hot exhaust gases. The engine oil, as we discussed, handles a significant chunk, maybe up to half in some engines, dissipated through the oil cooler. The rest has to be removed directly from the engine cylinders and heads by the air cooling system.
And that's where the fins come in.
Exactly. Those metal fins cast onto the outside the cylinder heads dramatically increase the surface area that is exposed to the cooling air flowing past. More surface area means more effective heat transfer away from the metal into the air through convection. Maintaining the integrity of these fins, keeping them clean and undamaged, is therefore vital for effective cooling. Broken or dirty fins reduce cooling capacity.
But just having fins sticking out isn't enough, is it? You need to ensure that a sufficient amount of cooling air is actually flowing over them, especially on the ground or in a climb.
Precisely. You can't just have stagnant air sitting around the hot cylinders. The engine cowling, the streamlined enclosure around the engine, and a system of carefully shaped sheet metal plates called baffles and seals work together.
How do the baffles work?
They are designed to block off paths of least resistance and force the incoming cooling air, ram air during flight or air pulled by the propeller, to flow tightly over and between the cooling fins of all the cylinders, ensuring intimate contact. They prevent the air from just taking the easy way out without picking up heat. They also create a pressure difference, high pressure in front, low pressure behind, to drive the airflow.
Okay.
Additionally, small tubes called blast tubes are often used within the baffling system to direct focused jets of cooling air onto particularly hot running components like the spark plug elbows, magnetos, or fuel pumps to prevent them from overheating.
And you also need a way to regulate the amount of cooling, because an engine can actually run too cold as well, can't it? Especially in descent or at high altitude.
That's absolutely correct. Just as it's crucial to warm up an engine properly before takeoff, maintaining an optimal operating temperature range during flight is essential. If the engine runs too cold, it can lead to problems like incomplete fuel vaporization, poor fuel distribution between cylinders, formation of harmful sludge in the oil due to moisture condensation, and potentially increased wear.
So you need controls.
Yes, aircraft engines are equipped with controls to regulate the flow of cooling air. Without these controls, an engine could easily overheat during high-power operations like takeoff and climb, and then become excessively cold during low-power descents from high altitude or in very cold outside air temperatures. Neither extreme is good.
What are the primary methods used to control the cooling airflow in these air-cooled reciprocating engines?
The most common method involves the use of cowl flaps. These are adjustable hinged panels, typically located at the bottom or rear exit area of the engine cowling.
How do they work?
By opening or closing these flaps, the pilot changes the size of the exit area for the cooling air that is passed over the engine. Opening the flaps reduces the back pressure and allows more air to flow through the cowling, increasing cooling. Closing them restricts the airflow, reducing cooling, and also reducing drag.
So you open them for climb, close them for cruise?
Generally, yes. Wide open for ground ops and takeoff climb when heat production is high and airspeed is low. Then gradually closed as needed during cruise to maintain correct temperatures, balancing cooling needs against aerodynamic drag. They can be operated electrically, hydraulically, or sometimes manually via levers.
Are there other cooling control methods?
Another system, less frequently seen on modern light aircraft but used on some older or higher-powered ones, is the use of augmenters or augmenter tubes. These devices use the high velocity of the engine's exhaust gases flowing through inner tubes to create a Venturi effect. This low-pressure area helps to suck or augment the flow of cooling air through the engine cowling and past the cylinders, improving cooling, especially at low air speeds. Sometimes the heated cooling air from the augmenter shroud was also used for cabin heat or anti-icing.
Interesting. Any other systems?
Some light aircraft employ a system often called pressure cooling. In these designs, ram air entering through carefully shaped inlets in the nose cowling is directed by tightly sealed baffles around the cylinders. The warmed air then exits through openings where low pressure is created by the slipstream, or sometimes by ejector tubes connected to the exhaust stacks, which help draw the air through. These systems can sometimes be effective enough to eliminate the need for adjustable cowl flaps.
What kind of maintenance do these reciprocating engine cooling systems typically require? What do mechanics look for?
Maintenance primarily focuses on the integrity and proper function of all the components that manage the airflow. That includes the cowling itself, the cylinder baffles and seals, the cylinder cooling fins, and any cowl flap mechanisms if fitted. And of course, monitoring the temperature indicating systems, cylinder head temperature, CHE gauges, oil temp, sometimes exhaust gas temperature, EGT gauges, is crucial as they provide feedback on how well the cooling system is working.
What do you inspect on the cowling?
The engine cowling needs to be regularly inspected for security of its fasteners, screws or latches, any signs of damage like cracks, dents, distortion, or tears. You also check any internal reinforcing ribs for cracks, and crucially, the condition of the flexible seals attached to the cowling that press against the baffles to prevent air leaks. Damaged seals let cooling air escape without doing its job. If cowl flaps are fitted, their hinges, linkages, and operating mechanism are checked for condition and freedom of movement.
And the cylinder fins themselves?
Cylinder cooling fins are vital. They must be carefully inspected for cracks, breaks, or excessive damage, like being bent over. There are usually allowable limits specified by the manufacturer for the number and size of broken fins, or how many adjacent fins can be damaged before a cylinder needs repair or replacement. Small cracks might be stop drilled and rough edges smoothed, but major damage compromises cooling. Keeping fins clean from dirt and oil is also important.
And the baffles inside?
The sheet metal cylinder baffles and the flexible baffle seals are absolutely critical. They force the air to follow the intended path close to the cylinders. They need to be inspected for cracks, especially around fasteners. dents, distortion, chafing against other parts, and loose or missing fasteners. Damaged or missing baffles can quickly lead to localized overheating of cylinders. Small cracks can often be stop drilled, minor dents straightened, but severely damaged baffles need repair or replacement. Ensuring the flexible seals are pliable and creating a good seal against the cowling is key.
What about the temperature gauges, CHT specifically?
Cylinder temperature indicating systems usually consist of the gauge in the cockpit, electrical wiring, and a thermocouple sensor mounted on one or more cylinders. The thermocouple is the critical part.
How does that work?
It uses the principle that joining two dissimilar metals, like iron and constantan or chromel and LML, generates a tiny voltage that is proportional to the temperature difference between the junction at the cylinder and a reference junction. This tiny voltage drives the cockpit gauge.
Where are they installed?
Common types are the bayonet probe, which twists into a well in the cylinder head, or the gasket type, which is a ring terminal fitted under a spark plug. It's usually installed on the hottest running cylinder as identified by the manufacturer, or sometimes multiple cylinders are monitored. You check the wiring for security and chafing, ensure the probe is installed correctly and tightly, and verify the gauge reads ambient temperature before engine start. A fluctuating pointer often indicates a poor electrical connection somewhere. EGT systems use similar thermocouples placed in the exhaust stream.
Moving on to turbine engines, you said internal airflow is absolutely key to their cooling. How does that work when there's continuous fire inside?
That's the incredible challenge. The continuous combustion process within a turbine engine generates enormous sustained heat, making effective internal cooling absolutely essential for the engine's survival, let alone efficiency. Temperatures inside the combustor can exceed 3,000 degrees, AFRI 1,650 degrees, far hotter than the melting point of the metal alloys used.
So how do they not melt?
Through very clever use of air. A significant amount of the air entering the engine's compressor actually bypasses the combustion process itself and is used specifically for cooling. Only a fraction of the total airflow is used for the actual fuel burning.
Where does this cooling air go?
This relatively cooler air, bled from various stages of the compressor, is directed through intricate internal passages to cool the hottest parts. It flows over the outside surfaces of the combustion chamber liners, often forming a protective film of cooler air on the inside surface as well, film cooling. It might pass through specialized center tubes within some burner designs.
What about the turbine itself? That must get incredibly hot from the exhaust gas.
Absolutely. Before the extremely hot combustion gases reach the first turbine stage, they are deliberately mixed with some of this bypass cooling air to lower the gas temperature to something the turbine blades can withstand with their own internal cooling. The turbine blades themselves often have complex internal passages where cool bleed air flows through, exiting through tiny holes on the blade surface, film cooling again, or trailing edge. Turbine vanes, the stationary blades, are cooled similarly.
So air is cooling parts from the inside out.
And the outside in. External inlets might direct cooling air onto the turbine case to control its expansion and maintain proper clearances with the blade tips. Compressor bleed air, as we mentioned with lubrication, is also ducted specifically to cool the main shaft bearings and other internal components. This spent cooling air eventually finds its way back into the main gas path and exits with the exhaust.
What about the outside of the engine?
The engine's outer case is typically cooled by the ambient airflow passing around it within the nacelle. In high-bypass turbofan engines, like on most modern airliners, the engine core and nacelle are also extensively cooled by a portion of the cool bypass air from the large fan at the front.
It sounds like managing all this internal air is incredibly complex.
It is. The internal compartments of the engine are often divided into distinct temperature zones, like the cold section compressor, the hot section combustor turbine, and various accessory zones underneath. Case drains are provided to safely collect and discharge any fluid leaks, oil or fuel, from these zones. Within the accessory zones, carefully calibrated airflows are managed not just for cooling electronic components or accessories, but also to purge any potentially flammable fuel or oil vapors. This purge air often comes from ram air scoops or fan bypass air, and pressure relief doors are incorporated as a safety measure in case of overpressure.
And sometimes you see insulation blankets on engines.
Yes, especially around the hot exhaust duct, tailpipe, or augmenter sections, and often around APUs. These are thermal insulation blankets, typically made of fiberglass material covered with metallic foil. Their purpose is to reduce the high temperatures radiated from these parts, protecting surrounding aircraft structure, wiring, and components from heat damage, and also preventing accidental contact with hot surfaces by maintenance personnel. They often have covers to prevent flammable fluids like oil from soaking into the insulation.
That's a truly fascinating look at how these incredibly complex engines manage to stay cool while operating under such extreme conditions. It's just amazing engineering.
It really is a remarkable achievement. The precise design and careful management of both these systems, lubrication and cooling, are absolutely fundamental to the safe, reliable, and efficient operation of all aircraft engines, whether they're powering a small propeller plane or a massive intercontinental jetliner.
So just to quickly summarize the key takeaways here, we've seen how absolutely crucial lubrication is minimizing friction, yes, but also dissipating heat, providing seals, cleaning inside the engine, preventing corrosion. That applies to both reciprocating and turbine engines, though the details differ.
Right. We explored the different types of lubricants, their key characteristics like viscosity and how it changes with temperature, and that whole evolution from simple mineral oils to the sophisticated synthetics and multigrades we use today.
And we looked at how the systems work wet sump versus dry sump, the critical components like pumps, filters, coolers, all those valves, and the essential maintenance practices needed to keep them healthy, including oil analysis like SOMP.
Then we shifted focus to cooling. We examined the huge challenge of managing the intense heat of combustion in both engine types. For recips, we looked at air cooling with fins, the vital role of cowling and baffles, and methods to control cooling like cowl flaps.
And for turbines, we saw how utterly critical that internal airflow management is, using compressor bleed air for intricate cooling of liners, blades, vanes, and bearings, all working alongside the oil system.
Exactly. These are incredibly intricate, sophisticated systems. Each presents its own unique set of engineering challenges and really ingenious solutions, all working together in concert to ensure that these powerful machines can reliably take us up into the skies and bring us safely back down again.
It really makes you appreciate the incredible amount of thought and precision engineering that goes into every single flight. So, looking towards the future now, thinking about the continuous advancements we see in material science, in engine design efficiencies, how might lubrication and cooling technologies continue to evolve in the aircraft of tomorrow?
That's a great question to ponder. Will we see even more advanced synthetic lubricants, maybe oils designed for even higher temperatures as engines become more efficient, or perhaps radically different cooling methods?
And what entirely new challenges might arise as we push for even higher levels of performance, or perhaps shift towards more sustainable forms of aviation, like hybrid electric or hydrogen power? How do you lubricate and cool those systems? It's certainly a lot to think about.
Definitely food for thought.
Well, if any part of this deep dive has sparked your curiosity, we really encourage you to explore the specific areas that caught your interest in more detail. There's always more to learn. Thanks for joining us on the deep dive.